Hi, I am Varun Joshi and welcome to day 19 of our Certified Kubernetes Administrator 2025 course. Today, we will master Kubernetes requests, limits, and limit range to prevent noisy neighbor issues and ensure fair resource distribution. What you see on screen is a Kubernetes cluster that consists of two worker nodes, node 1 and node 2. Each node has 6 virtual CPUs and 24 GB of memory. There are two deployments in this cluster, deployment 1 and deployment 2. Each deployment has 2 pods and each node has 2 pods from each deployment. Each pod in this cluster has a single container. Everything is working smoothly, but suddenly deployment 2 starts to malfunction. There was something problematic in the code and both the pods of deployment 2, that is this pod and this pod, they start consuming all the resources of the node. When they start doing that, what happens is the deployment that was working fine, that is the containers of deployment 1, they also start facing resource crunch because all the resources that were available for node 1 and node 2 were being used by the containers of deployment 2. Hence, deployment 1 pods were also starved of resources. We want to avoid this situation, and this is where requests and limits come into picture. So what are requests? Requests are minimum guaranteed resources, typically CPU and memory for a container. What are limits? Limits are a ceiling which says that the maximum resources a container can use. Let's do one thing. Let's define requests and limits in our containers so that we can tell the containers that this is the maximum you can use of this resource and hence maintain stability in our Kubernetes cluster. Let's scroll down. Now this diagram looks good to me because in this diagram, all the containers have a resources section, and that resources section defines requests and it defines limits. Request says I want CPU as 1. Before diving into it, when I talk about CPU, if you talk about physical servers, you would hear the concept of CPUs. If that machine has hyperthreading enabled, then the 12 physical CPUs are equivalent to 24 virtual CPUs or 24 cores. If hyperthreading is not enabled, this CPU is equal to 1 is for 1 physical CPU. In case hyperthreading is enabled, which usually is, if I talk about any cloud deployments or even on-premises deployment where you would see that your Kubernetes cluster spreads across virtual machines, there you will talk about virtual CPU. In that scenario, this CPU number represents the virtual CPU. Simple. If hyperthreading is not enabled, this is 1 physical CPU. If hyperthreading is enabled, then 1 is the virtual CPU, or you can call that core. And we are saying memory is 2 GB bytes. So we are reserving 2 GB bytes for requests. Then limits, we are saying the maximum that this container can use is 2 CPUs and memory is 4 GB bytes. This we are defining. Now, once you define these things for all your containers, then deployment 2 pods, even if they malfunction, the containers running in these pods cannot go beyond the defined CPU and memory. We will see what happens when containers go beyond their defined requests and limits in a little while. But once we do this, there are several benefits. So benefits of using requests and limits. First is efficient resource allocation. Ensures resources are optimally used across the cluster. Second is avoidance of resource starvation. Prevents one workload from hogging all the resources like we saw. Here, the containers that were part of deployment 2 were hogging all the resources. Third is cluster stability. ensures Kubernetes can efficiently schedule and manage workloads. Since everything has defined requests and limits, I will not face resource starvation because of other pods consuming all the resources. Then the last one is mitigation of noisy neighbor problem. In this particular node, when deployment 2's container started to use all the resources, then this container became a noisy neighbor because this container was creating problem for the container that was running for deployment 1. Hence, mitigation of noisy neighbor problem prevents workloads from disrupting others. This is what we have seen thus far. So hence, the conclusion of what we learned from this is you should always define requests and limits for your containers so that the resource utilization can be tracked and maintained. Now, Varun, we are talking about containers and pods. Where exactly do you define requests and limits? See, your pod can have multiple containers and we define requests and limits for each container because your pod could be running 5 containers, for example, and each container will have its own memory and CPU requirements. Hence, you should define requests and limits for each of your containers. But in 1.32 release of Kubernetes, if I go to this documentation, you will see that you can define, I'll just zoom in, you can define pod level resource specification in version 1.32 as well. So if I talk about requests and limits, you define them within a container. Okay, so you see that this pod has 2 containers. One is named app, the second is named log aggregator, and each container has defined requests and limits. These are defined at container level, but with Kubernetes version 1.32, you can define these at pod level as well. If you see this example, here they have defined the limits and requests at pod level as well. And when you do that, this defines how much your pod can utilize. My recommendation will be to define requests and limits individually for each container. Let's go back to the diagram now. So we have understood the benefits. We understand what requests and limits do and what they are for. Before I move ahead, I want to explain one more thing. Requests and limits can not only be defined for just CPU and memory. There are other resources as well for which you can define requests and limits. I quickly want to show you what those resources are. I am in the GitHub repo of this lecture, day 19, and you see that you can define requests and limits for CPU, memory, along with these 4 other things. Usage of top 3 is very common, but these are project specific, and I will let you read the documentation to understand what these are. I want to discuss quickly about ephemeral storage. Each node that is in your cluster can have its own storage as well. Typically, what you would see is you would be using storage that is coming from NFS, SAN, or any other external medium, not the internal storage of the VM or the node itself. However, by default, your containers, your pods will be storing logging and other data in the node's internal storage itself. Hence, you want to control how much of ephemeral storage your containers can use. And for that purpose, you can define the ephemeral storage that your pods and containers can use. If I go here and I search for ephemeral, then you would see that you define ephemeral storage in the same way like you defined for memory and CPU. You see requests here, you see ephemeral storage. It says that only 2 GB bytes can be used, and similarly under requests itself you can have CPU and memory, and similarly in limit as well you can have CPU and memory along with other resources that we have discussed here. So I hope this is clear. I'll go back to my diagram. I'll scroll down a little. Now let's understand a few more concepts. When I say this container is requesting 1 CPU, this applies that the minimum resources that this container requires is 1 CPU and 2 GB of memory. Right now, my node has 6 vCPUs and 24 GB of memory. If I spin up 3 containers like this, right now my node 1 is running 2 containers, hence 2 vCPUs are reserved for these 2 containers. In case I spin 6 containers in this node which have a request of 1 CPU, then all the resources of node 1 will be utilized. If I try to spin a 7th container, no matter if it requires half a CPU or 1/4 of the CPU, then that pod will not be scheduled onto this node, because the scheduler will see a resource constant there. If I show you day 15 here, we discussed that scheduler has certain considerations before assigning node name property to a pod. We already discussed taints and tolerations, affinity and anti-affinity. And the first one here is resource availability. How does the scheduler know how much resources are available in the node, and how much resources does the pod that I'm about to schedule in a node requires? How can scheduler know these things? Scheduler know these things because you would have defined requests for your pods, for your containers. If in this scenario scheduler sees that there are requests made by 6 containers of 1 CPU each, then it knows that node 1 is already exhausted, because whatever you see in the request are the minimum requirements for that container to run. If I scroll up here, requests, minimum guaranteed resources, typically CPU and memory for a container. And what we saw here is, if the resources are exhausted, then another container, another pod will not be scheduled onto node 1. Okay, then what are limits? Limits are a ceiling. For example, if this container wants to use more than 1 CPU, then it can use up to 2 CPUs as long as 2 CPUs are available in the node. If there are resources available for the node, a container is free to use up to the limits defined for it. For this container, the memory limit is 4 GB and the CPU limit is 2. As long as the node has resources, this container can overshoot till the limits defined for that container. Then let's see what happens if container tries to go beyond its requests. We know if it tries to go beyond its request, then it can go beyond if the node has resources up till the limits. But what happens if a container tries to go beyond its limits? When it comes to CPU, the kernel throttles the CPU. I want you to concentrate on the word kernel. I am not saying kubelet, I am not saying Kubernetes, I am saying the Linux kernel throttles the CPU. If it tries to go beyond 2 vCPUs, if it tries to use more CPU cycles, then the Linux kernel will throttle that to 2 CPUs. That's understood. When it comes to memory, it says the kernel, again, no kubelet, no Kubernetes. The kernel may terminate the pod. The keyword is may. Now, why we are using may? Memory pressure. If the node does not have enough memory and the pod is still trying to consume more memory than the allowed limit, then the pod is killed. OOM killed. OOM implies out of memory killed. If there is no memory pressure in the node, the pod continues using memory beyond its limit. So if node has enough resources, then the pod can continue to use memory beyond defined in its limits. I want you to take this with a pinch of salt, because we are going to do a demo and then we'll come back to this point again. Whatever I'm defining here, there is an asterisk mark to it, and we'll see what the asterisk is once we go to the demo. So let's now go to the CLI. I am in day 19, and to check the current utilization of my resources of my nodes, I will run kubectl top nodes. This is the first time we are using this command. This works similar to top in Linux. Here we are just adding kubectl and then the nodes, because we want to check the utilization of the nodes, which is why we are typing nodes. If it were pods, we would have written pods. Now I'll press enter. What it says that the camera is obstructing my view. Error, metrics API not available. What is this? Why it is not available? So I will take back you to day 7, where we discussed the Kubernetes architecture, and we also discussed control plane components and data plane components and what role they play in maintaining your cluster and how they function when you create a deployment. If you have not seen this lecture, I would highly encourage you to first watch day 7's video, refer GitHub notes and come back here. So we discussed few add-ons here, and the first add-on we discussed was metrics server. What is metrics server? Now kubelet is running on each worker node. We know that. And kubelet collects the information about the node and about the pods. So kubelet is collecting the metrics, CPU, memory and other metrics for both nodes and pods. And kubelet is sharing that information with the metric server. But the error that we saw here is metrics API is not available. This implies that currently the add-on metrics server is not configured, which is why when API server is sending a request kubectl top nodes to the API server, it is asking those details from the metrics server, but it sees that the metrics server is not available. Hence it is giving us this error. So what we want to do now is we want to configure the metrics server. And before we do that, I quickly wanted to explain one more thing. Here we did an oversimplification that kubelet collects all this data. What really happens is kubelet binary has C advisor as well. And this C advisor is container advisor, and container advisor exposes an API, and that is the API that collects the metrics from both nodes and pods. Saying that kubelet collects was an oversimplification. Now we know kubelet has a component called C advisor that collects these metrics, and then kubelet delivers these metrics to the metrics server. And once you have metrics server configured, then kubectl top nodes will work seamlessly. So what we will now do is I'll go to my GitHub repo, I'll scroll down a little, and here we know how to install the metrics server. You can just go to this link, or you can simply Google install metrics server on Kubernetes. I do this, the first link, I'll go here and then I'll scroll down. In the installation section, it says kubectl apply -f. Now we could have used this, but there is a small argument that I want to add. I want to add --kubelet -insecure -tls. Now this flag is necessary because kind clusters use self-signed certificates, which the metrics server does not trust by default. So what we'll now do is we'll download the YAML for the metrics server, and then we'll add this line, and then we'll simply apply that. No rocket science. We just go here, and here we can just quickly just copy this part up till the latest. I'll Control C, I'll Control V, and I'm here, and you can just click on this YAML and it will get downloaded. So I have already downloaded that and I have kept it here. Here is my components.yaml. Let's do one thing. I'll quickly zoom in, zoomed out. I've zoomed in, and these are the contents of this YAML. I'll quickly copy this --kubelet insecure TLS, and you have to paste it in the deployment section. This is the deployment. There is only one deployment that this YAML will create, and in the arguments you add this line here. I've already added this. You should just add this and save this file. And once you do that, let's do a walkthrough. See, this file contains a lot of objects which we have not yet discussed, like service accounts we have not discussed, cluster roles, cluster role again, role bindings, cluster role bindings. We have not discussed these yet, so you can ignore these. Just run this file for now. And you also have a service being created. Then there is a deployment, and we have added this part in the deployment YAML. And then if I move ahead, it also creates an object with the kind API service. I'll go to my terminal and I will run kubectl apply-f components.yaml. I'm in day 19, and in day 19 I have this file. I have applied this file and it has created these many Kubernetes objects. If I run kubectl get pods -n kube system, then I will see that there is a pod running for metrics server and its age is just 21 seconds. Now if I run kubectl top nodes now, I see that now I am getting the CPU and memory utilization statistics for my nodes. If I run kubectl get top pods, I will see that I'm also getting the CPU and memory utilization for my pods. To show you this, I created a deployment, and that deployment has 5 replicas, and it is showing 5 replicas and it is showing the utilization. You see that Nginx consumes so less memory. It's just using 8 MB per replica. So I'll clear my screen quickly. Now I want to show you one more thing. I'll run kubectl get pods -o wide, and I see that majority of my pods that are 3 replicas are running in worker 2. So let's do one thing. I'll run a describe in this node, kubectl describe nodes, and it is my second cluster worker 2. I'll press enter, and you see that if I scroll down, okay, these from here we have seen that we can see labels here, annotations here, taints we have already seen. But if I move down, I also see a table that tells me what my pods have requested and what are their limits. So if you see, none of these pods that are part of my front end deploy have defined CPU or memory requests or limits. But if you see, the kind net, which is part of my kind, they have defined their requests and limits. And then the memory is 50 MB, and the limit for memory is also 50 MB. So here is the place where you can see all the requests and limits. I'll now clear my screen. I'll now go to Visual Studio Code. I'll open memory.yaml, and you see here is a pod manifest like we have seen before. We are creating a container. That container's name is memory demo CTR, and the image that we are using is polinux/stress. Stress is a utility that is used to simulate memory load, and which is what we are going to do now. Then we have a resources section. This is something that we are seeing for the very first time. In the resources section, we are defining both requests and limits for memory. For memory, we are saying that this container requires 100 MB, and that should always be available for this container. When scheduler sees this pod, it will only schedule this pod onto a node that has minimum 100 MB of free memory. Similarly, we have also defined limits, and that is the ceiling, the maximum that this container can use, that is 200 MB. Now what we are saying is, we are also running a command stress, and the argument for that command is 190M, that is 190 MB. We are giving this a load of 190 MB. So let's go back to the CLI, apply this manifest, and see what is the utilization of this pod. I'll run kubectl apply-f memory.yaml, and I see a pod is created. I will now run kubectl get pods -o wide to see where this pod was scheduled. This pod is running and it was scheduled in cluster worker 2. I will now run kubectl top pods, and I see that this pod is using 193 MB, and if I go here, that is the maximum that this pod can use. This pod will not go beyond 190. Let's run this again. and I see that it is not going beyond that, and the limit for this pod is 200 MB bytes. Now what I will do is I'll change this figure to 250 and then let's see what happens. I'll make this 250. I will name this pod memory demo 2. I'll save this file. I will go here. I'll again run kubectl apply -f memory.yaml. I will run kubectl top pods, not top pods. I'll run get pods -ovide. Wait a minute. What I see is OOM killed, but that's contradicting to what we just learned. We learned here that the pod is only killed if the node is facing a memory pressure, and our node has ample resources. Then why was this pod OOM killed even when the node had no memory pressure? Strange, right? I want to introduce the concept of control groups here. I'll go to my diagrams again. I'll scroll this down a little, and here you see these are all the worker nodes, and let's say this is our worker node 1. What is control group? Firstly, forget Kubernetes. We are talking about a Linux concept here. Control group is a Linux feature which says that if there are two processes, then one process is supposed to use these resources and another process is supposed to use these many resources. So control groups essentially create resource boundaries, and those resources could be memory, CPU, hard disk, IO, and so on. In case any of the process tries to use resources beyond what is defined, then the Linux kernel kills that process. Okay, this is about Linux. Now let's get back to the topic in hand, that is Kubernetes. Here is the kubelet. We know that kubelet receives the instructions from the API server that this is the pod that I want you to create, and this pod has these containers, and these are the specification for these containers. Kubelet invokes the container runtime. A container runtime could be containerd, cryo, podman, and there are many more. So the container runtime pulls the container image from the registry if it's not already cached. Then it configures networking using the CNI plugin, mount volume specified in the pod definition, creates and starts container inside the pod. These are the responsibilities of the container runtime. Container runtime also creates something called a control group for the container as well. Irrespective of the resources section in the container or pod, this C group is created for every container. When it comes to resources section, for example, if I talk about the pod that we just created, this pod defines both requests and limits, and there is a control group that is managing these limits and requests. When Linux kernel sees that in a control group there is a process that is using more than the defined limit, then the Linux kernel kills that container. In our example, the Linux kernel kills that pod. I want you to understand that for the Linux kernel, if you are running 10 pods, 50 pods, all of those are just processes, and the core functionality of Linux kernel is to kill anything that goes beyond what's defined in the control group, in the C group. Hence, your pod which used beyond the specified limit got killed. Okay, Varun, we understood that. Then why does the documentation say that a container will only be killed if there is a memory pressure in the node? Some Linux kernels are relaxed and may allow the container to run even if they go beyond the specified limit. But the kernels I have worked with and any environments I have seen, they all kill the pod, OOM killed, if they try to use more memory than specified in the limits. CPU gets throttled. If memory container tries to go beyond the limit, then it gets killed. If you go to the Kubernetes documentation, they mention this here. If I move to the top, they say that memory limits are enforced by the kernel, by the Linux kernel, with out of memory kills. When a container uses more than its memory limit, the kernel may terminate it. However, terminations only happen when the kernel detects memory pressure. We have seen the opposite of this. There was no memory pressure and kernel still terminated it, because Linux kernel, whenever sees that the memory is used beyond the limit, it kills it. But there are certain kernel configurations that are flexible in nature. They may allow to use memory beyond what is defined in the limits. So I'll leave this here and let's get back. So what we saw was, as soon as memory was beyond the limit, the container was OOM killed. Now what we can do is, if I again run this command, I will see that this has gone into crash loop back off, because the kubelet is trying to restart this pod again and again. Let me do one thing. I'll run kubectl delete pod memory demo. We have deleted this. I will leave it like it was before, 190M, and then we can go here. If I run kubectl top pods, you see that this pod continues to run just fine, and it will not go beyond this, because the limits that are for this pod are 200, and here we are only giving it 190 megabytes of load. I'll clear my screen, and I hope this concept is clear to you. Now let's try it for CPU. I'll go to Visual Studio Code. I'll open this file. This is again a similar demo. Here what we are saying is, the request is of 500. The limit is for 900M. What does M mean? If I talk about CPUs here, let me give you this example. One CPU is equal to 1000 millicores, okay, and it is denoted by M. So if you write 1000 M, it is equivalent to 1 CPU. If you write 500 M, that is equivalent to half CPU. If I define 250 M, it is equivalent to one fourth of the CPU. If I define 100 M, that is equal to 1/10 of a CPU. So you can also define CPU with millicores. If I go here to my documentation, here also you can see this distinction. Yeah, 500 M means half a CPU and 900 means 0.9 CPUs. That's understood. So let's do one thing here, that this means 0.9 CPU. I'll remove this from here, and then here we are saying that we are giving it a load of 1 CPU. However, the limit is set to 90 M. So ideally you should see that CPU is throttled at 900 M, and this one figure or 1000 M you will never see, because we know that Linux kernel throttles the CPU if it tries to go beyond the limits. So let's go to the CLI. I'll run kubectl apply -f cpu.yaml. It's created. I will run kubectl top pods, and here I see that pod is created, but it has not yet shared any metrics with the metric server. The kubelet has not shared the metrics yet. So let's run this again. Okay, not yet shared. Let's give it some time. 1, 2, 3, 4, 5 seconds. Okay, we see the CPU demo here now. It says that it's using 898 M. So we have specified the limit at 900 M. It will not go beyond 900, even though in the arguments we have specified that you are supposed to use 1 CPU. It is not allowing this container to go beyond 900 M. If I again run it, I'll still see 900 M, but it won't go beyond this figure. So I hope this is understood. If I run kubectl get pods -ovide, I see this is running on worker 1. So what I'll do is I'll run kubectl describe node I'll do it for worker 1, and then I can see in this section as well. CPU demo requests are 500 millicores, limit is 900 millicores, the request is 0, and the memory requests and limits are 0. So we can see this here as well. So if you want to see what all pods are running in a node and what are their requests and limits, you can see that in this section as well. So I'll clear my screen now. We have discussed this. What else I wanted to discuss? But Varun, I have to define requests and limits all the time. What if there is an administrator which creates a new pod and that pod does not define any requests or limits, then what happens to that pod? That pod can run on this node, and then if the code is faulty or because of XYZ reason, it can again consume all the resources of the node. These containers will be at loss because they have defined requests and limits, but still there is another pod that came in and used all the resources. How can I prohibit that situation? You will always have this scenario wherein you will see pods that do not define any requests and limits. What you can do is you can define a limit range object at the namespace level, which will ensure that any pods that are configured will have some values for requests and limits. Those some values are defined in the limit range object itself. So if I go here, I run kubectl API resources, I see that there is a limit range object somewhere. Yeah, limit ranges. The kind is limit range. Namespace is true, which implies that for every namespace, you will have to create this limit range object. Since we are working in the default namespace right now, I will configure the limit range object in the default namespace itself. So if I go back to my Visual Studio Code, I have already defined a limit range YAML. I'm naming this as resource-limits, and API version is v1, and we know that we can check API version, kind, and short name, or whether the object is namespace using kubectl API resources command. And then we have created this. Under spec section, we have limits. And under limits, we have limits is a list, and the first type is container. And for container, we are defining if someone spins a container, the default CPU and memory limit will be this: 2 CPUs and 4 GB bytes of memory. Then default request for CPU and memory will be this. And then what we have also defined is if someone spins a container which has requests for CPU and memory higher than these, we don't allow that container. And we have also defined the minimum. The minimum CPU and memory request for a container should be these. If it is less than this, then don't spin that container. So let me just quickly apply this. kubectl apply -f limitrange.yaml. If I now run kubectl describe limit ranges resource-limits, that's what I called it, it tells me that what are the CPU and memory default requests and limits, and it also defines the minimum and maximum for them. It is imperative that you also define minimum and maximum along with what will be the default for requests and limits. Now if I, let's say, create a container now, kubectl run my pod, and my pod will use image of engine X. If I press enter, this says that my pod is created. If I now do a describe on this pod, kubectl describe pods my pod, press enter, and if I scroll up, I see now the request is 1 CPU 2 GB bytes and limit is 2 CPU and 4 GB bytes, and this is what I specified: 1 and 2 and 4 GB bytes. I hope this is understood. Now let's do one more thing. Okay, I'll quickly clear my screen. kubectl get pods. Let me delete these pods. kubectl delete pods, memory demo, my pod, and CPU demo. Let's delete these. These are now deleted. I will go to my CPU, and in this what I have written is the minimum for CPU is 500 M. Okay, this is what the minimum request should be, and here the request is, let's do it 400 here. And now let's see what happens. I'll control S and I'll go here. It's still deleting. Okay, kubectl apply -f cpu.yaml. I'll press enter. Error from server: when creating CPU pod, CPU demo is forbidden. Minimum CPU usage per container is 500 M, but request is 400 M. So you see, it is not allowing us to create a container which has the request lower than 500 M, as 500 M is the minimum that you must be requesting. I hope you understood this concept, and understanding requests and limits is very important because it's a Kubernetes best practice to have resources section for your containers. All these come under best practices. So you should always have requests and limits specified for your containers. And now Kubernetes also support you to have pod level requests and limits. And I've already told you my preference is to use requests and limits for each of your containers. And you should also refer the GitHub notes. This explains everything that we have discussed thus far. I think that's all I wanted to cover. Let me see if something else is pending. No, I have covered most of the things. That's a wrap for day 19. But there is more to resource management. In the next lecture, that is day 20, we will build upon what you learned today and jump into Kubernetes autoscaling. We will cover horizontal pod autoscaler and vertical pod autoscaler. If you have any questions, feel free to ask them in the comment section and I will reply. If this helped, do consider liking, sharing and subscribing. It will mean a lot to me. Thank you very much.